Good evening to all of you. Myself Deeposri Saha, Assistant Professor of Elitte College of Engineering and the moderator of today's session. It gives me immense pleasure to extend a very warm welcome to all the participants, esteemed resource persons and all the dignitaries to the fourth day of ATAL FDP on modeling and simulation of composite materials, fabrication, characterization and applications, organized by the Department of Mechanical Engineering, Elitte College of Engineering. Today we have gathered here for the seventh technical session which focuses on composite materials engineering, its fundamental principles, material systems, applications, and crucial role of steel in modern engineering practice. For this enriching session, we are fortunate enough to have with us a highly accomplished academician, researcher, and industry expert as our guest of honor, Dr. Jayanta Saha. It is my proud privilege to introduce Dr. Jayanta Saha to this esteemed gathering. Dr. Saha is a renowned specialist in steel applications, corrosion engineering, fire engineering, and advanced industrial coatings. He holds a PhD from Jadavpur University and MTech from IIT Madras and a BE from Bengal Engineering College and brings over 4 decades of rich experience spanning academia, industry, research, and technical leadership. Currently, he serves as the Chief Technical Officer at Asianol Biotech Private Limited, is a visiting professor at Jadavpur University and the University of Calcutta. He works as a freelance technical consultant to several industries. He is the author of a Springer published book titled Atmospheric Corrosion, has compiled 22 technical guidebooks, published numerous research papers, and contributed to major industry reports. Dr. Saha is actively associated with BIS committees, the CII Corrosion Management Council, and various international steel and corrosion associations. His contributions have been recognized through several prestigious honors, including the NACE India Corrosion Awareness Excellence Award, the Mascot National Award, and SSPC Awards. With great respect, I invite Dr. Jayant Kumar Saha to kindly commence the session. Sir, please.
Yeah, thank you.
Welcome, sir.
Professor Deeposri Saha. Good evening to all, respected, participants, and special thanks to Elitte College of Engineering. Of course, Professor Animesh Talapatra, he was kind enough to include me for such a great program as one of the resource persons. I must say I'm privileged to be the part of this program. Now with this, let me share my screen. I'll just you want to take any photograph right now, or because of the bandwidth problem I will be just closing the video, or you want to take at the end?
Sir, you may carry on.
Okay. My screen is visible to all?
Yes, sir. Is it visible? It's visible, sir.
And yeah, audio level is okay?
Yes,
Yes, sir.
it is okay.
Right.
Please
Thank
go
you.
ahead with the PPT mode, sir.
Yeah.
Okay. Yeah, it's good. It's okay, sir. Thank you.
Yeah, so today, I think today is the fourth day. Last 3 days, you have a lot of deliberation on the different subjects. Today's subject will be slightly different, and it is one important subject. Whatever structures we are thinking of making, I will be mostly dealing with the infrastructures where different types of materials are being used. But with the present scenario, you will find there are a lot of external influences are there when you are going to design. like sustainability, like recyclability, low energy bodied materials. So all those things, and at the same time, people expectation, the life cycle cost. So thereby, the conventional way of making infrastructures today, it has become very challenging. And there comes the composite materials, and how this successful blending of composite materials with the steel, you can do wonder. I will be taking you through that journey only, how and what are the advantages of the steel, disadvantages of the steel based infrastructure system materials, and then how composite can come in, and then there are certain disadvantages of the composite, because of that you have to go for the hybrid systems. So my basic title for this today's presentation is a composite materials in engineering. We'll be talking a little bit about the principles, applications, and the role of steel. What I said just now, the infrastructures does not fail by strength alone, it fails by the materials misalignment. The word misalignment, I said, few decades back, we are only talking about the steel. When we think about iconic or landmark structures, people used to use the construction grades of steel or the mild steel. Unless otherwise, compelled by a very harsh environment, like highly corrosive environment, industrial environments, then you can go for slightly different types of materials, maybe FRP, maybe stainless steel, depending on its merits to survive in that situations. So thereby the basic material remains the same as on day steel, because it's a durable, it has got a very good ductility, and it is predictable. Its life can also be predicted, provided you provide the adequate protection systems of the steel as well as the adequate fire protection system to the steel. But the today's challenge is not on the strength. We are talking about the performance. That means the structures has to survive very hostile environment. Think about industrial structures, think about the offshore structures. So those challenges are different in natures. And at the same time, because of the environmental policies, there are a lot of challenges. You cannot go for continuous way of sandblasting, to go for good type of coating every year. There is a atmospheric pollution is a issue. You cannot consume or you cannot manufacture a higher quantity of the steel, because it emits carbon dioxide to the environment. That is also a challenge. So all those things has to be addressed in one place, very systematic way. So India, if you see the major part of the infrastructures as on date, still it is happening on exclusively on the steel, except few areas where you will find some composite materials are taken. I'm talking about not that steel, the concrete type of composite material. I'm talking about the basic steel along with some FRP or maybe metal matrix. So that type of things is taken care. So the future is not the steel versus composites. The future is the intelligent integration of both. So the today's session, I will talk about mostly the infrastructures material, and then how we are evolving durability, sustainability demands, exposed to the limitations, and complementing steel with the composites, and validating its performance through the advanced simulations. Hybrid material systems emerge as the most resilient and future-ready solutions. Now, I'll just go through. These are the agenda points we'll just touch upon. Uh, Introductions, evaluation of the material, then the steel, the backbone of the infrastructure systems, the performance challenges and the limitations of the steel structures, emergence of the composite materials, and then limitations and recycling challenges of the composites. So we say that one major point for the steel to be used for any projects, we pitch for the steel is 100% recycled material. Every time, not a single gram of steel gets wastage, because you have to recycle, you melt it. Now there is another dimension is added to the system, that you cannot consume more energy. So we have to consider that part, recyclability part also coming into the picture. So thereby steel is also taken slightly backseat when we are talking about the energy consumption. While manufacturing steel is also high energy consumption activity, the same thing is applicable for recycling of the steel also. So steel composite integration, we call it as a hybrid system. That is the ideal solutions as of now. So role of the modeling and simulations and digital tools are inevitable, and we will just touch upon what are the future things are coming, or in the advanced countries they are following this type of practices. In our country we are yet to catch up. So basic requirement for any modern infrastructures, maybe building, maybe bridges, maybe flyover, maybe railways, transportation systems, maybe the transmission tower, offshore establishments. Everywhere, three important aspects are there, three or four. That is a high strength material has to be used. It has to be minimum weight, and the durability aspect of the life expectancy should be very high, and ultimately leading to the cost efficiency. So all those things, if you see, the steel is scoring negative mark because of the it's a higher density material. So it often fails to meet all the performance requirements. There comes the entry of the composite materials. And these composite materials, we all know that engineering property can be tailored depending on our requirement. So in composites, you will find glass or the carbon fibers offer higher performance, but there is a catch. The cost and ductility is a limitation. Those are the issues for that composites. So steel remains the essential due to the reliability and economy and compatibility, or maybe the constructability with composites. So modern design increasingly use hybrid materials, and it's all about the same. So earlier days, what as a metallurgist people used to do, that just open the specific diagram, we call it the SB diagram, find out the material which serves my purpose with respect to the stiffness, with respect to the UTS value or the ductility value, and then the corrosion protection uh, you know uh, facilities available for that type of environment. So those things are nowadays as not the only criteria. Now we have to go into the material integrations, and that material integration has to be the material moment you are doing, that cannot be done because it's a metallic material, non-metallic material. You have to use the extensive use of various type of models and simulation technique to validate the material properties. So these are the basically three things you will find: the durable structures enablers, the materials, the first one. Then you have to have a very good design parameters, and then third is the protection parameters. So all those things leading to the durability of the structures. Now, the second one, if you see the durability with respect to the right kind of material. So we only know the mild steel or the construction grades of steel. There are other varieties like weathering steels, maybe high strength, low alloy steels that you have higher UTS values, and those are aligned with various type of Indian standards. The mother standards are IS 2062, IS 800, or maybe Indian Road Congress 24. So this protection, the third parameter is the protection. It is as crucial as the strength of the material, because the corrosion is something like cancer to the steel. That depending on the environmental condition, you never know corrosion how it is spreading inside the material, and there are cases you can have a catastrophic failure of the materials or the structures. So thereby, these are the three things we have to consider for the durability of the structures. Now, when we talk about the backbone of the infrastructure system, you think about any landmark structures, whether it has been made 50 years back or it is a recent, any structures, it stands on these four pillars. What are these pillars? First one is the material, what you are selecting, or the design, what you are doing, it has to be very safe. That means the proper workmanship and the construction of the materials. Then the durability, it has to be in a good design so that whatever activity you do, you can do at ease. There are, cases when you will find the accessibility becomes a problem, weldability becomes a problem. So all those things are considered under that. And the third one, when you are going for the steel-based structures, the one of the prime requirement, it has to be elegant, it has to be sleek. So aesthetically, it is a good one when you compare to concrete-based constructions. And the last parameters in every project, it is the cost effectiveness. So this is how the steel stands out as a construction material, ensuring safety, enhancing durability, and optimizing cost and enabling aesthetic excellence. Just few seconds back, I talked about the SB plot for the optimal selections of material. Now, this is a very, some sort of, Bible to the material scientist, because you open and find out, uh, because in the design says that I want this type of, modulus of elasticity, this is a specific strength. So in this chart, you will find all sorts of materials are placed. So from that, you can choose the right kind of material. Now here you can see, only thing is you see the polymers and then the metals and the composites. So in chronology order also, this as the chart says that composites are having and a higher level than metals with respect to certain parameters. But when you go for the construction, it is not only those parameters. So in infrastructure, there are other parameters also has to be considered. So the compare and the select materials by the stiffness to weight or weight to the strength to the weight ratios. It is not only the criteria, it also has to be the lightweight and high performance design choices. Thereby, the judicial compositions of metals and the various type of composites serves this type of purpose. So we have to have a, now all those things have been done through the simulation and modeling. But earlier days, this used to be done from the SB plots. Now, naturally, the question can come to all of your mind when we have a very high strength material, so it becomes a lightweight. Because if you see the right side, the automotive industry or maybe the aerospace industries, they are using very high strength metallic materials. So it can go up to 2000 MPa value. When we talk about the steel structures, infrastructures, we are only happy to use maybe 400 to 600 MPa values. Because if you go higher, then weldability and fabrication becomes an issue. So that is the reason it is restricted to a specific strength class. But at the same time, the moment you go for the lower strength, your weight for the structures increases. So if there are compulsions to reduce the structures less weight, then you have to have a mutual what should I say, the mutual arrangement with the steel and the composite materials. So that's how these things is taken. So I said that the high strength for the mobility like automotive and maybe the aerospace industries, but the control strength for the infrastructures. The reason behind is the weldability and fabrication ease. Just to give you little idea about, because we all know, but I understand in this session, there are people, they have very good knowledge about the steel, but at the same time there are experts who are not having much idea about the what type of construction grades of steel or maybe the different types of other steel. So I put this slide for them only. It just, if you think about any alloy, iron and carbon, from the iron carbon diagram, it can be classified in three parts: low carbon, medium carbon, and high carbon. So the carbon percentage is mentioned. If you add that in the iron carbon with manganese, chromium, silicon, vanadium, etc., or the chromium, all those things are giving you another steel, we call it the alloy steel. So we have a three different types of alloy: low alloy, medium alloy, and high alloy. Any steel having more than 10% of alloying elements, we call it the high alloy. Stainless steel is one of them. Because in the stainless steel definition, it has to have more than 10.5% of chromium. So that's what this is, that structural steel we are only concentrating this part, but the stainless steel is also used in various applications as a infrastructure material. Now these are some of the steels following industrial practices as per the Bureau of Indian Standard Codes. So these are the grades of steel. Of course, 2062 it talks about 750 grades, but not all the times we are using those type of materials. Now, how these steels are made? These steels, the construction grades of steel, or maybe any material, we are talking about the composites. You can draw an analogy also from this, that the any structures you made, it is through the structures, property, and the performance. You first know the performance. The material has to give this type of performance. For getting this performance, what property the material should have, and then to get this type of property, what should be the structures? So I have just given this analogy. When you are processing the composites or the hybrid material, all those methodology or philosophy has to be considered. So it is that the three things, that the material performance governed by interplay of the processing, how you are processing, what structures you are achieving through that processing, and then what properties you give, that leads to the performance. And that performance is nothing but influencing the durability, strength, and the long-term reliability of the structures. So this type of informations are there for our relevant codes. We call it as a mother code for IS 800 and IRC 24. These are the two mother codes. I have given an extract, but here nowhere it talks about the present infrastructures facing the problems made with the steel with respect to the life cycle cost, with respect to the very harsh environment. It talks about this type of environment where you can find out corrosivity categories, but not beyond that. That means you have a restricted life of the structures. So I will be taking you through various advancement where this type of corrosion issues has been taken care. This type of high density materials or the higher dead weight of the material can be taken care by using various type of composites. Now, having said so, by this time you have a fair idea about why steel is used as a construction grades of material, but it is not immune from the corrosion. That is also known to us. Now, let us see about this performance challenges and the limitations of the steel structures. The steel's limitations are environmental, as already I mentioned, the two important issues, that the material has to be, consuming less energy. It should also consuming less energy during recyclability, and it also gives very high performance with respect to number of years. So all those things steels cannot give all the time. So thereby the limitations I have just noted down in one place. There are 5 to 6 major limitations the structural steels are having. What are these? Continuous corrosion from the moistures, chloride, and pollutant. That means you can ask that a question, that if I go for the galvanized steel, if I go for galvanizing the top of that organic coating, yes, that gives a life of the structures for a limited period of time. It's not an infinity. It is not the life of the actual structure. If the steel structure's life is say 50 years, it is not giving 50 years. It may be giving 3 years to 5 years to 7 years. But after that, you have to go through the blasting of the entire systems, which sometimes become very difficult. Think about the left side images. It is made of the steel, but can anybody do blasting without causing nuisance to the environment? Answer is no. So this type of challenges the existing structures are facing. So because of that, there is a shift in the thinking process, that how to make infrastructures more durable, and durable with a more number of years against a very harsh environment. The second one is very high life cycle cost. as I already mentioned, repenting, difficult access to the complex steel geometry that I've already mentioned, that one, environmental and safety issues, coating degradation in the marine and industrial atmosphere. And whenever you go for every time the maintenance, that is the disruptions or the downtime of the production or maybe the occupancy. So all those things are nowadays people are very serious about that. Just look into this very interesting slide. This is not a single one, is a new construction. But when all this construction number 1 to number 5 were made, that time it was landmark structures. Maybe today also it is a landmark structures. But the structures are having various type of corrosion issues. So people have developed various type of systems to cater and to see that the structures is performing longer life. So what are these things? Golden Bridge, they are the frequent painting is also due to the marine salinity. Sydney Harbour Bridge, atmospheric corrosions, and in Australia there are a lot of regulations on the blasting processes. So you cannot just do nuisance to the environment. So all those things are basically creating various type of obstacle for the structures to stand still for a longer period of time. And then the last one, if you see that offshore and oil and gas platforms, this severe splash zones and seawater, naturally there will be a challenging environment. So there also you will find that people started using a lot of composites in that area, because composites is immune to most of the time from the corrosion. So this is how the modern infrastructures, when people are thinking about, they try to address all those things, taking clue from the existing structures. So that is the learning for the new designers, that what it should be. If we put all those things in one place, there are three challenges that steel infrastructures are having. What are the challenges? The design part. In the design, it is not only it gives very good aesthetic part, it gives a maybe high strength grades of steel you use compared to the low strength grade of steel, you get light structures, you can have adequate corrosion protection, you can have adequate fire protections, and all those things. You can have wind design, you can have seismic design, and fatigue considerations. So these are the things continuously evolving out, and new challenges our designers are facing. The same thing for the fabrications, and the last one is the corrosion protections. Because when you see various type of complex pollutant environment, it is very difficult to address with the conventional coating systems. I mean the ceramic based coating, I mean the organic coating, I mean the metal coating, or maybe the hybrid type of coating. So those are the coatings have got limited life with respect to that environment. So these are the challenges. Now, how to go ahead with that? So there are specific uses of the composites, so that we get material immune from that corrosions for a longer period of time, which steel alone with the coating cannot provide. So that much is about that limitations of the steel. And then the composite materials. Now these composite materials, it is not the replacing steel with the composite, which cannot be. So it is basically complementing each other so that you get maximum value in terms of the performance. So we talk about that is a time to look beyond steel used for the infrastructures alone. These are the points already I've highlighted, that energy intensive productions and the recycling, escalating the maintenance and the life cycle cost, and the highly vulnerable in the aggressive environments and requires frequent inspections and repainting. So the solution is that intelligently integrating composite with the steel. So infrastructures can achieve high performance and durability while significantly reducing the life cycle cost and environmental impacts. Just to know little bit about various type of composite materials. The again, I'm just giving some preliminary informations on this, just to recapitulate what it is and how it is formed. Maybe few slides may be repetitions for the last uh, 3 days what you have been following. Excuse me for that. So this is the composite materials is basically engineered material made from two or more constituents. First constituent we call it the matrix, and the second one we call it the reinforcement. So you can see the side photographs, the reinforcement and matrix you make the composites, and they have their specific purpose. So when you see that fiber or the reinforcement, it provides very high strength, high stiffness, the low density, and the matrix, it gives a good shear properties and the low density. So when you combine both the things as a composites, you get high strength, high stiffness, and good shear properties and the low density. So this is the basic structures of the composite, and the property is superior to the individual components, stronger than both. So that means if you consider steel or the composites, you will find the steel as a matrix and the other material as a reinforcement. So put together, you will have better strength if you see the individual materials. So ideal example is the reinforcements. Even you can see that RCC reinforced concrete. That is a very old technology. The example of the composite construction. Now, when you see this graph, there you will understand that the two most popular metallic material used for various applications, steel and aluminium. When you compare with some composite materials, you can see this, the weight, just as a comparison, thermal expansion, stiffness is very high, strength is also high, the fatigue resistance is also high. So this is some of the properties for which the composites are considered. A little bit of historical development. If you see this, when it started, the first one is in the right side. You can see that straw reinforced mud bricks, ancient time, and then improved strength. The crack resistance was the issue for that, and then we developed fiberglass, FG, FRGP, GRFP, the carbon fiber composites also, the lightweight, high strength applications area. Now, today we are talking about hybrid composites. That means the steel and FRP, steel or concrete systems, or various type of smart composite adaptive properties are also there. So this is, they are not exactly all those things are for infrastructure. There are various other automotive and aerospace industries. A lot of composites are used, and those are in the smart composites. Now, if you see the composite material, earlier we talked about there are two constituents in a composites. One is the matrix phase, and other one is the reinforcement phase. So matrix means, as you can see from this, image, it is a continuous phase, and it binds and protects the reinforcement. It is holding that reinforcement in the system and transfer load between the reinforcement and protects from the environment. So these are some of the examples of polymer, metal, and ceramics, because the name says these are three types of matrices are made. In that, reinforcements are added to that. So the reinforcement phase is a discontinuous. As you can understand, reinforcement various types. So it is a discontinuous phase. They are not connected each other. Provides strength and stiffness, can be fiber, particle, and flex. That is again the type of reinforcements, and it governs strength and stiffness. Example is the glass fiber, carbon fiber, and steel fiber. So you just look this slide for a few seconds, that a matrix phase and the reinforcement phase. What are the materials we are used as a matrix, sort of materials form we can use as a reinforcement phase. So here you can see the composites, the particle reinforced, fiber reinforced, and the structural reinforced. And there you will find in most of the cases nowadays in India, whatever structures, some material people are using. So those are, I'll just take a pointer here. Mostly the laminates and sandwich panels, those are used mostly for the infrastructures. So in other areas, not much having application as of now in the Indian infrastructures development activity, because we are mostly going for the 100% steel. We are going for the steel and concrete as a composite. We are going for various type of FRP decks. So only that much, but not many. But you will find there are a lot of laminated sandwich panels are used as a partition materials, not as a load bearing member for the structures. So we said the three type in the matrix. You have seen that the two ingredients for the composites. One is the matrix, and other one is the reinforcement. Now in the matrix, you will find there are three different types of matrices of the composites. Basically the polymer, we call it the PMC. Then you have a metal matrix composite, the MMC, and the third one is the ceramic matrix composites, which is CMCS. So these are some of the examples. You can just, I'm not going to read this, but there are certain advantages of this each and every type of matrix what you are using. The first one is a polymer. Naturally, it is a lightweight, and being a non-metallic material, it is corrosion resistance very high degree. And the being a metal matrix, you have a very high strength and temperature resistance. When you are going for ceramic matrix, you have excellent high temperature and wear resistance. So thereby, depending on the situations, depending on the applications, you have to choose the matrix for the composites. So that's what you will find for the application to aerospace or the thermal protection systems. We use the silicon carbide or aluminum, that type of ceramic material as a matrix, so that you have very high degree of temperature resistant. So this is again a snapshot of what I said in the earlier slide. This talks about that. In one line, what I can say, there are merits, there are demerits of earlier all those three things, that PMC, MMC, and CMC. The PMC faces the thermal limits, CMC suffers from the brittleness, and MMC's constraints are manufacturing complexity. The moment you are using the metal matrix in that, so you have a manufacturing complexity, it requires very high cost. So lack of mature data, design data is not available as on date. So that causes hindering for the adoptions, because people are always looking identical design, and the manufacturing easiness, so that the material can be fabricated and can be fixed to the system. So in the absence of both the things, it becomes difficult to implement that type of technology for the infrastructures. So that part is a matrix. Now the second ingredients is the reinforcement composite. Reinforcement, what are the reinforcement? There are three types of reinforcements normally used. So this is again the second constituent. We call it the fiber reinforced composites, particle reinforced composites, and the structural composites. As I already mentioned, the structural bearing composites are basically sandwich panels, laminated composites. These are all used mostly for the infrastructures. And fiber reinforced composites, this is again the reinforced concrete. There are glass fibers reinforcement bar. If you search in the Google, you will find in India there are few metro construction, metro railway constructions, mostly in the Delhi area, has been using the glass fiber reinforcement bar to replacing the steel reinforcement bar. And there are certain reason behind that as a experimental, and as of now, the structures are not stressed. So but only thing, there are issues for the fabrication, there are issues for that, but again, it is not very popular in our country. So the fiber reinforced composites, that is the one area. The fibers may be continuous, maybe discontinuous, but when you are talking about the RCC based construction, it is a continuous, because the fibers has to move entire strength of the beams and columns, or maybe the decks. It is basically continuous. And coming to the particle reinforced composites, again, it improves hardness and wear resistance. And the last one is the structural composites, built from the layered sandwich structures designed to load-bearing applications. High stiffness, the low weight, and this fiber reinforced component. Now you have seen the three types of reinforcement component: fiber, then particle, and then structure. If you go to the fiber, it has got again two types, as I already given example with the reinforcement. So the continuous fiber or maybe the discontinuous fiber, it has got its own advantages and disadvantages. So I'm not going to read, but only thing, it's the moderate strength, the better isotropy if it is a discontinuous fiber, and continuous fiber used for the load bearing capacity is critical. So that's what I said. The metro railway constructions in Delhi area, lot of composite reinforcement bars have been used. So those are basically not metallic material. It is purely a non-metallic material used for this type of constructions. So you can see the fibers, what you are giving, and you can have this three types of composites: the steel fiber reinforced composites, glass fiber reinforced polymer, and the carbon fiber reinforced polymers. So these are the three things. And the right side bottom what photograph you can see, this is the fibers, how it looks. And in other type of constructions, people have started using the steel wire mesh in this concrete construction to replace this type of thing. Better advantage you can get using the steel fibers, because that prevents the micro crack propagation in the structures. So it gives the better strength. The right side, I need not explain. This is a self explanated images, continuous and aligned fibers. You can see this discontinuous and aligned fibers, and the discontinuous and randomly oriented fibers. So these are the three types: continuous, discontinuous, or discontinuous, the randomly oriented fiber. This also can be arranged during the manufacturing process. So you get still better property with respect to the discontinuous, because in discontinuous it is aligned. So here it is randomly, that means it has got more resistance, so it gives the better strength in some cases. The second part is the particle of the second and third type is a reinforcements, is a particle composites and the structural composites. Particle composites, you see this provides very high compressive strength and durability. Example is the cement matrix. In the cement matrix, what we provide, we give the sand and the stones if you are giving. So that becomes the aggregates particle. So sand and aggregate particle and cement matrix, it becomes a classic example for the particle composites. And laminates, yes, the right side you can see this type of laminated, or we call it the sandwich panels. These panels, the top and bottom, you can have the steel sheets, and the inside you can have a composite materials. So through this, you can improve the material strength, you can reduce the weight, and at the same time, you can also have very good property with respect to the fire rating. The minimum coating thickness will give a very good fire rating of the this type of sandwich panels. So these are the applications. As I said, out of these three types, the structural composites, those are basically used as of now mostly for the building, bridges, marine and automotive structures, and of course for the aircraft panels. Aircraft panels means the wing and other places we call it the honeycomb structures. There all these composites are used. Now, how this, we have seen so far there are two major constituents. One is the matrix, another is the reinforcement. What is the mechanics of this? So it is basically a three ways it helps or increase the property when you compare to the steel. Number one is the load sharing mechanism, interfacial bonding, and the stress transfer efficiency. These are the three important part. So here on the right side, if you see this, this is how the structures composite, that is an example of that. You can fiber, there interface, and there is a matrix. Now, in this way, you can have one after another layer if we are talking about the laminated composites. Now, what it does, the fibers carries most of the applied load and matrix supports and distribute the stress. And the interfacial bonding between these two layers has to be very strong. Otherwise, there will be a failure. And the same way, the stress transfer will depend on that. The better bonding, the higher composite strength. If these things are not managed through this design, then you have a failure of this fiber. You will have a crack in the matrix. This is the matrix. There will be crack in the matrix and failure in the fiber and matrix disbonding. That means when it is a fiber and matrix are there in the system, if they are disbonding, so you can have also a failure. So composites making or manufacturing is not like what a isotropic material like steel or aluminum is made. It's a very I said say it's not a very easy technology. It has to evolve continuously, and that's why depending on the property you are looking for, depending on the strength, or depending on that other parameters, it has to be developed. So that's what it is not like that a conventional material you just mix it, put it in the furnace, you do it proper melting process followed by casting, and then you go for the rolling and you get the material. It's not that. So the failure modes of the composite, just now what I said, you see this is a layer to layer. If the interlayer bonding is not enough, you have a delaminations, you have a debonding, you have a matrix rupture, and other like pull out and all, and the fiber ruptures. In the earlier slide, what I have shown it here in this image, those things have been exploded, and it is shown like this. As I said, the manufacturing is very difficult just to find out the its structures versus property versus performance. So it's very difficult job to design a composite material to serve the purpose. So we follow always the rule of mixtures. So in the rule of mixtures, basically to predict the mechanical properties of the composites. Based on the properties of the fiber and the matrix, we know if we take this type of fibers, we take this type of matrix, and then there is a ratio of that. Strongly depends on the volume fraction of the constituents. So in this case, how it is calculated, we see, suppose we put this type of fibers, 1, 2, 3, 4, 5, maybe say 5 fibers. It is shown very enlarged view. Now in the fibers, if you put to in terms of the volume, the matrix is the total is 100. So if the fiber you put together, this volume becomes F. If it is the total is 1, so it is 1 minus F. So 1 minus F is this. So the volume, important tool for design and optimization of the composites, and increasing fiber volume fractions generally increase the strength and stiffness, assumes perfect bonding and uniform stress distribution. That is also to be considered. So it is not so easy. As I said, it's very easy. Go into the rule of mixture. Just you take proper ratios, search the literature, put that both the things, and you start making the composites. Not so easy. So this you have to find out the optimum level where your desired properties are achieved. Now, if I take you to the next, then you will find how difficult you have to make this type of charts, continuously making these to make one the rule of mixtures applied for elastic modulus of the composites. So there you can find there is the upper bound and there is a lower bound. So you have to find that what strength you want and what is the elastic modulus you are achieving at that point. So this is that, depending on that, you have to do continuous experimentation to finalize the rule of mixtures. That means what should be my ratio of matrix and the reinforcement, and then other parameters will come in. That means this, what is the strength, what type of reinforcement I have to provide. So all those things becoming a system is very complicated. Now, if you see this, there are, as I said earlier, there are three types of composites: the PMC, MMC, and the glass fiber matrix. So there you will find that if you compare with the conventional materials, the temperature gradient increases from the polymer to ceramic. As I said, in the ceramic you have a lot of ceramic materials. So those ceramic materials, due to that, the temperature retention is very high. So this is again another this type of chart from where you will find that specific strength of the material at elevated temperature. The steel loses its elevated temperature strength the moment it crosses maybe 450 to 500 degrees centigrade temperature. Thereby, the requirement for at this strength up to 450, you need to have fireproofing coating for the steel. But when you develop a component in such a way that that type of coating may not be required, because the composite takes care that part. The same logic goes for various type of analysis. I'm just giving some of the idea behind composites, because it gives some idea about that. When you compare with life cycle cost for 20 years projected life, there you can find the initially the composite cost is higher, but at the same time you will find installation cost is lower, maintenance cost is frequency is reduced, so maintenance cost is low, and the replacement and downtime cost is almost negligible. So thereby it scores over the steel based constructions. And the same way, and I have already mentioned that why the Delhi Metro has used, the answer is here, because to try out with this, the glass reinforced fiber uh, polymers reinforcement bar is used, because it emits during manufacturing low CO2. So that is the reason, and it has got other advantage, though the joining was the issue, but there are various systems through which you can join reinforcement bar continuously one after another. So it becomes a continuous reinforcement. So shows significant reductions in CO2 emissions when GF, GFRP is used, particularly at the optimized spacing. This is again some analysis I have taken from internet, and that report says this is the reason for this. So just to summarize this composite, this part with a few slides, then we will go to the hybrid systems. This composite is stronger than metals for the same weight that you have seen in the earlier chart also. Resistance to the corrosions and the environmental attack is lightweight for the design efficiency and maintains performance under repeated loading, means that it has got a better fatigue resistance property. And right side you can find various type of reinforced these composites with respect to the steel and high strength steel. So this is again some of the equations that FRP plus steel equal to lightweight, efficiency into ductility, safety and long-term durability. So this is how you can compare the FRP fiber reinforced polymer uh, is always better with respect to the steel and aluminum. So this is some of the few charts I have put. Uh, this is not to be discussed much on this. Only thing, the advantage of the composites FRP, if you see this, the with respect to the corrosion resistance, yes, it is good. Weight, yes, it is good. Strength to weight ratios maybe higher than steel. Installation time and the cost, maintenance needs, lifespan, thermal conductivity, design flexibility, and environmental impact. So all these areas you will find the FRP is better than the conventional steel, but only thing, the manufacturing part is a issue. And then in the industrial, uh, all these calculations, people are only seeing the cost of the material. If the cost of the material is higher, then people go for can absorb the hidden cost. So that's how the since in our country we are not still adapting the life cycle cost analysis basis the selecting of the material. So in the life cycle cost analysis you have to consider each and every aspects. It costs to the society, it costs to the amount of energy it consumes, it causes, it also considers when it is going into the recycling or the dumping, what way it gives an difficulty to the society. All those things are calculated. So there is no regulations to consider, but however this as on date this is the good idea to go for that whenever it is possible. So this is again, already I've talked about the energy absorption capacity. So there again, right side photograph, you can find the steel connections versus GFRP connections. Because if you see that energy absorption capacity, that gives a better protection in the seismic applications. So we call it the energy absorption capacity. The material has got a higher, it can consume, it can take more shocks. So that means for the seismic zone also, this type of composites where you have high energy absorption capacity with respect to the steel, or the area which has to be providing that type of support, that components can be made with the composites. So for the seismic resistance structures in abroad, people have started using various type of composites for taking this type of advantages. This is some of the left side you can see some of the engineering applications where this composite materials are used: high performance resins, adhesives, carbon fiber based materials, then lightweighting, advanced polymer composites, biomaterial, nanocomposites, smart metal composites, additive manufacturing, circular material economy, and intelligent design manufacturing. So I just keep this slide for 30 seconds. If just go through that, and then I will go to the next one.
Hello, sir.
Yes.
Sir, sorry to interrupt. If possible, can you please turn on your video so that we can take a couple of photos of your session?
Okay. You can take.
Yeah.
Just to come out. Want to take photograph. Okay.
Yeah. with your presentation slide.
Okay, right. Now how to go that slide? This I have to make it short or what?
Yes.
You are sharing the screen. No, but you have to go out, no, from that
Yes.
scheme.
Okay, okay, okay.
Otherwise, that's what. Yeah, yeah. Now,
Yeah.
and now you are screen sharing. You are sharing actually. My screen is it visible?
Sir, your screen is visible, sir. You
But
just minimize the zoom, and then your screen will be visible. PPT
okay,
will be visible.
my video is
Yes.
seen now.
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes,
Now
sir.
it
Okay.
is
It's
okay.
So
Now it
there's
is
a
okay.
little confusion. Now we can take the photograph.
Yes, sir.
Right. So we are in this composite materials in engineering applications.
Thank you, sir.
Yeah, as I told you, that these are the areas, major applications. If you have a just a look on the right side, the major application, you see that most of the cases you will find it is automotive, aerospace, energy, electronics, but there are cases, bits and pieces, maybe they are in infrastructures. That means infrastructure, that is the area it is catching up. But because of certain, problems, if you talk about infrastructures, yes, there are areas like, crash barriers for the all national highways. It is not only the steel, because the steel has got its advantages, but when there are non-metallic materials made with the composites are also a part to the crash barrier systems, so it gives the better performance in case of casualty. So this type of infrastructures areas people have started using, but not in the high intensity. This is a very interesting slide. If you see this in the composite market, now you see these projections. It started in 2019, and it is this curve shows the historical data. It is, and it is also predicted that the use of composites will be growing every year at the rate of 8.61. So that means the nearly tripling, about 290 by US billion dollars by 2035. I mean, this is the value. Think about this composite materials, and you see the percentage of this almost here you can see the carbon fibers is the highest, and the glass fiber, and then the third is the other metal matrix and all. So all those things are not much will be increased. So other composite materials will be higher in percentage. Now, we talked about so many good things about the composite materials, but yes, there are certain drawbacks in the composites. So we have to maintain the high performance that brings new challenges. What are the challenges? I think somewhere I mentioned that recycling is an issue for the composites. Now, number one is the cost. The manufacturing cost is very high. If you're going for very high-end, high performance composites, the complex manufacturing process, inspection difficulty, detecting internal defects or micro cracks is harder than the steel structures. So that is a also getting evolved, that inspection methodology for the composites when it is in service. But in the steel, you can have various type of gadgets are available. Through that, you can detect, like RCC based structures. You can find out, you can repair it, or even the steel structures. You can take that in situ metallography. You can have the checking of the various type of mechanical properties, and you can provide a suitable retrofitting of the system. But in a Composite, yes, those are the areas still it is workable on that. And the last, not the least, is the recycling issues. The separation of the fibers and the matrix is difficult, limiting the recyclability. That means since it is a composites, that means there is no process through which you can recycle it. You have to separate out two components. So this is the reason, I give an analogy that when a ship is completing its life, its entire journey, maybe 30 years sailing through the sea, it comes to the shore for ship breakage. Now, all the major or developed countries, they have stopped breaking the ships in their land. Reason behind, because in a ship, you will have different types of metallic material, including steel, aluminum, titanium, whatnot, copper, all those things, along with various type of composites, ceramic materials. So, and at the same time, textile, everything is there. So those materials separation is an issue, and always there is a chance of mixing the material. So thereby, these are the areas, recycling issues. The recycling hub is the only three countries in this part of the world. These are the India, Bangladesh, and Sri Lanka. So these are the areas, all the ships throughout the globe coming to this point for the breaking. So this is again a recycling issue. So I am giving the recycling. The word, when we are talking about the normal steel, it's very easy. Just break into pieces, put in the furnace, and it goes for the making the new steel. But in case of a composite, it's not so easy, because you need to have a method to separate each and every grams of fiber from the matrix, and then only you can recycle it. So that is one of the issues. But the bottom line is composite is chosen for the weight savings, corrosion resistance, and to give a Taylor property. So that thing, because of three major criteria, composites are still used, though you have about 4 limitations. So I call it as a paradox. So I said it is a very good thing, but at the same time it provides high performance, but it produces the waste, which that waste, it is basically cannot be recycled. So the lower embodied energy and carbon footprint, these are the positive points: high strength to weight ratios, good corrosion resistance, reduced maintenance and extended service life, widely used in the infrastructures, transport, and renewable energy. But the thermoset composite poses serious end of life challenges, and the global GFRP market is growing, that you have seen in the earlier slides, up to projected figure 2035. And the wind turbine blades, the major contributor to the composite waste. And if you have seen that the wind turbines in India, it is not many. There are 2-3 companies they manufacture for Indian installations. But if you see in the developed countries, in Europe, you will find in America, there are a lot of wind energies installations are there. Those are basically, I have some figure that how many wind blades will be discarded, wind turbine blades will be discarded by this year, mid of this year, and limited recycling routes for the thermoset composites. So this is some of the, one side it is good, but at the same time, there are some issues. For that, the technologist has to think it over. Should we use further, unless otherwise we find a proper solution for the recyclability of these composites? Should we go further or not? So that is a question for that. So the challenges: the thermoset polymers are cross-linked and non-meltable. That is the key word, non-meltable. Conventional recycling routes used for the thermoplastics do not work. End of life management remains a major sustainability, and the market projected that you have seen earlier. And now this is a figure I'm talking about: 19,000 wind turbine blades expected to be retired by mid 2025, because it has got a fatigue life. So the fatigue life, so many lakhs of cycles. The moment it is completing, because of the safety requirement, the turbine blades, wind turbine blades has to be discarded. And it creates huge waste which cannot be recycled. The wind sector alone generate 85,000 tons of thermoset waste and the fiber properly. So this is the issue, and we consider this a challenge for using the composite. So with this having said so, this type of material cannot go directly for the infrastructures. Now the solution is there are very costly recycling processes are there industrially, but it's not very commercial skill. So we call it the pyrolysis, solvolysis, and the mechanical recycling. But there are issues for this. So when you compare with the steel, it's highly recyclable, but again, energy is an issue, energy consumption. Composite recycling, these are challenges. And then you have a future eco-design strategies, thereby people are all talking about whenever you are going for any big project, people are talking about the circular economy. That means how the material is giving performance throughout its life and how it is going to be disposed at the end of its life, and all those things are calculated. Now, this is that area where I said that it's a very complex process. There are two ingredients. There are so many parameters, and then you have to see that it is matching with the steel, and at the same time it gives it take over the difficulties the steel is having. So thereby the system becomes very complicated. Then the role of modeling and simulation is a must for this type of situation. And it is more so because in conventional metallic materials, it is an or maybe other material, you have the isotopic properties of the material. But in composites, it is an anisotropy in nature. That means the direction dependent properties, mechanical properties like strength and stiffness vary with the fiber orientation. And again, the advantage in the tailored design, specific direction, you can provide the more loading, which you cannot do maybe the axial direction. If you want the more loading, you cannot do with the steel or aluminium. But there are challenges. So careful considerations, calculations, and simulations due to the non-uniform behavior. So that this is the basic reason why the simulations and modeling is a must for designing the composite materials, because of the anisotropy material, and we want to have a tailored properties with respect to the axis. That also is possible through this type of process. Now, I have not done any work on the modeling. Just for sake of this, I just give you some idea about this, because you have other sessions where you are listening from the experts on the how the simulation model is working, how they are validating, how they are doing digital twinning. So I'm just giving an idea that why this modeling and simulation is must for the composite materials, as I said, due to the anisotropic behavior of the material. And the experimental testing alone is very expensive. That means if you make that design, then do the prototype in the conventional way, testing it, and it failed, go for the second one, third one. It becomes a very laborious, time intensive, and costly experimentations. So the modeling enables the virtual material characterizations, performance predictions, and the design parameters optimization. So it is essential for the modern engineering and certifications that this modeling and simulations of composite materials is a must. So there are three ways to do it. We call it the level of modeling. That is a micro scale, there is a meso scale, and the macro scale. The fiber is a micro, the ply level is a meso, and when we talk about the laminar level, we call it the structural response to the component is a macro scale. So this is the composite behavior is governed by the interaction across micro, meso, and macro. So these all three is a part of the composite materials connected through the bottoms up homogenization or the top down homogenization. That means you can go from left to right, or you can go from the right to left during the modeling stage. So this is the same concept. I just put that photograph here: micro, macro, and meso. So so this is not much to be explained here. In the earlier slide, the same thing. It is how it is done. This is a 3-stage, and then we have a multi-scale. When you are taking individual, then you can have micro, macro, develop the product in the uh, modeling through top to bottom and bottom to top, as I said that. Or you can have all three together for the best performance. The micro scale that gives some value on the structural level, then macro scale. Micro scale is a constitutional level, and the third one is the meso scale, is the ply or yarn level. So these all three can be run together. Various type of softwares are available for this, and I'll just show you. Maybe it is not the one a lot of people are using. There may be some others also. So the common analytical model rule of mixtures that we learned about, that classical lamination theory and shear lag and simplified micromechanics model. So this is some of the things I found in the textbook, and then these are the models like finite element analysis model. Then you have to find out the failure criteria and the common software tools. This is some of the listing I have just provided, but I have not done any hands-on on this. For the sake of this presentation, I thought it is worth mentioning these things, how and what type of softwares are being exploited, and then at the same time what type of failure criteria, as we have seen that if the proper matching of matrix and the fibers are not there, reinforcement, then you come across this various type of failure. As you've seen that the matrix failure, fiber, the reinforcement failures, interbond failures. So all those things can be captured visually through the failure criteria using this type of softwares. So this is again some of the photographs, nothing to be mentioned. Simulation of the web and composite, I got it from some source. So this is some of the simulation technique. Twinning, you all must be knowing digital twinnings. Earlier days in our time, we used to make prototype. It takes a lot of time. Now through this 3D printing or maybe the various type of digital platforms, you can make the digital twinning. I find some of the good side. It says that 5,51,000 twins have been made by this one of the companies. For these various type of structures, components, very complicated components, and the prediction of the failure, they made the twinning. And this is that just to give an idea that this is the simulation is a strategic enabler for the composite engineering. I call it that unless otherwise you have this idea about that, it is very difficult to develop and go further. Now, the last part of this is a steel composite integrations, hybrid systems. We'll go through this. So in composites, we have found that disadvantages. So we switch over to the hybrid systems as a practical solutions. So they are steel as a reinforcement. You can use that. You have seen that as RCC. There you can use the fibers, reinforced fibers, steel fibers also can be used, various type of decks and the floors, or maybe reinforcement bars. So you call it as a steel as a reinforcement. Steel as a matrix, steel can also act as a matrix phase with other fibers. So ceramic and polymer can be embedded in the steel using the metal matrix composites for high temperature and high strength applications. And steel in hybrid systems, that is a polymer and glass, allows a tailored property, and it is basically balancing the weight and the mechanical performance. So there's 3 ways the steel can be used for the composites. So steel as a reinforcement, steel as a matrix, and steel in the hybrid systems. So here the steel metal matrix composites, again the same particulate reinforcement, short fiber, continuous fiber, and continuous sheets. That is the laminations. So there are certain advantages. You can see that the wear resistance you can generate or increase higher when the surface is continuously rubbing. So you have a very hard surface. Use various type of metal reinforced particles that increases the wear resistance. Then the structural integrity means the load transfer and toughness can also increases. Reinforcement delays the crack initiations and propagations. Already I've discussed in case of the reinforced concretes, or when you are using fibers, or when you are using wire meshes, the micro cracks can be prevented for the uh, extending the micro crack. If the crack is there, it remains at that point for a longer period of time, unless otherwise the stress level is increased. And the high temperature capability also increases when you add different types of fibers in the steel. So this is how on the right side you can see the stackability. So you can have a steel and then you can have a fiber. Right side image you can see those things are mentioned. So depending on the type of property you are looking for, the stacking can also be arranged with the laminar, or a situation where you have a lot of corrosivity problem. You can have the fibers at the two end. So I'll show you another figure. There you will find fibers at the both the end, which prevents the corrosion even very harsh environment. So this is how the materials are selected. This is again a conventional steel fibers, reinforced concrete. You can see that this type of steel fibers are there, and these are the advantages: the crack arrest, improved ductility, and impact resistance. I'll not read all those things. Here again, I'm giving for your reference. I believe this presentation material you will all receive. So I just try to put all this information in one place so that you can, whenever you feel, you can just refer those materials in one place. So I request the organizers to share this presentation to all of you, those who are listening, because not all the slides I'm going line by line. So you can, it is a self-explanatory hybrid FRP versus steel system, the performance at a glance. So these are the areas for the infrastructures. The composite hybrid composite system is used: steel concrete composite girders, steel fiber reinforced concrete. Already I've mentioned that one, and hybrid steel FRP systems, concrete filled steel tubes. In India, maybe one or two infrastructure project has been made, but in Europe and America, there are a lot of big structures are coming. I'll show you some photographs. And steel sandwich parent system. This, of course, used in our country. So this is again in civil application. You can see that deck is made with composite slabs, and the girder, the steel reinforced or the hybrid. So all those areas you will find bridges, retrofitting, and reinforced concrete systems. This one you can see this, that depending on the outside, the fibers is FRP is there in the outside. This cross section is shown. Inside is the core, and then the concrete is filled inside. So the concrete will be taking compressive load. Inner steel tube will have this primary load bearing, and outer FRP jacket, it gives the confinement and the durability and the strength enhancement. That means even you have seen that metro and elevated corridor, this type of constructions are preferred. So you can have a concrete infill steel tubes covered with the FRP jacketing. So this is the type of, we are talking about the infrastructural use. The same one, what type of, FRP orientation, that fibers, how you are orienting, is a 0 degree, 45 degree, or 90 degree. The load carrying capacity also changes. This is a composite polymer This is again some of the analysis. I'll not go into this. So last few slides, the way forward and future of the infrastructure materials. So far, what we learned, that it is not only the steel, it is not only the composites, serves our purpose when we are thinking about the high service life, free from downtime, or consuming the materials which emits a lot of CO2, or maybe the material which is exposed a mild environment, corrosive environment, but tomorrow it will be facing very severe environment. So that type of thing process has gone. So it is not only one material. So I call it as a mono material, but intelligently hybrid it should be, and that material has to be made digitally enabled and life cycle driven. So that is the key for this today. That infrastructure material and various processes are there in industrial applications. You will find advanced joining, interface technology, hybrid structure and functional systems, incorporation of the smart and adaptive materials. So these are some of the things, and one more, that AI-driven design and engineering optimization, digital twins and predictive engineering tools, the machine learning and performance and life prediction. These are the some of the 6 areas. The continuous development is happening for the design team, just to find out the best material for its uses for the infrastructure or maybe other allied areas. And it is more in the aerospace and the automotive industries. So these are the areas where the research and industry outlook, increasing demand in infrastructure, yes. So there you will find the more and more the composite or hybrid type of systems will be used as and when, or the availability of the materials at the same time steel composite hybrid gaining importance. And this basically is not the job of the metallurgist, job of the mechanical engineers. It's a multidisciplinary research focus is going on. So integration of the material science, structural engineering, and data analytics. These are the some of the areas the research can is going on and can be taken up. So this is how the future trends. Nano reinforced systems, digital material design. So these are all those things you must be knowing. Only thing, and things are changing very rapidly. Maybe 10 years back, the type of material, type of practices, industrial practices we used to do, today, because of the availability of the AI, machine learning language, machine learning, all those things have been changing very fast. So the material evaluation is also not in the back seat. So it is, people are also taking the advantage. So I think I have covered more or less. It is almost 7:30, so maybe the next speaker will be waiting. So I conclude, the steel to stay relevant in the future, it must evolve with emerging materials and intelligent technologies. Now, the final conclusion is the composites redefine engineering possibilities, steel remains indispensable, and the future lies in hybrid and the smart materials. Because we are talking about the self-cleaning material, we are talking about self-healing materials, there the corrosion issues will not be there. So that type of technology is being evolved continuously. Only thing, the technology has to be the cost competitive. Technology will not cause any nuisance to the society. Those are the areas people have to look into. So with this, I conclude my presentations. Thank you so much for the patient hearing. If you have any, you can note down my email or the mobile number. If anyone has got any specific interest or further related informations on this, there are a lot of things have been talked about steel. So if anyone has got any specific interest, may not be on this subject, you can just write to me or you can call me, just mentioning that you have attended this program. So once again, thank you so much for giving a patient hearing. And again, I convey my gratitude to the Elitte College of Engineering and the entire team, a special to mention to Dr. Professor Animes Talpatro. He was very kind, and he have been informing us regarding the program. He has helped us to formulate this entire presentation. Thank you so much.
Thank you, sir. First of all, I want to say that there are very much appreciation regarding your presentation. You can check one comment like, sir is as strong as in composite basics and research like Amit Shah in politics. So it is very much delighting. So, thank you, sir, for your highly informative session. It was extremely insightful and very helpful in understanding the current areas of research and emerging interests in this domain. I now invite the audience to raise their queries. You may unmute yourself and ask sir directly, or you may post your questions in the chat box. Thank you once again, sir.
Okay, you have at 7:30 is another session.
Yeah, sir. So,
Hello, just I want to ask you something. It was a very informative session, and actually some questions are prevailing on my mind. That in
Yeah.
the industry, in the steel, when we are using as a structure, we always use this fireproofing. So
Yeah.
in this case, if you are using hybrid material, then how do you actually do the fireproofing? Because that was an issue which we faced actually. So we were not successful there. So can you throw light on that? And what are the limitations of the temperature to be used for the hybrid system?
Yeah, see, whenever you are using a material, let me know, first, you are from which organizations?
I am from Techno India University.
Okay, okay, okay.
Hmm.
Good. So basically, if you see this for fire proofing activities, it has got three dimensions. One is the fire resistance time. Fire resistance time is number one. Number two is the fire load. That means how much combustible material the container is having. And number three is the type of installation. Installation means that fire rating is a function of installation. That means if it is a hospital, the fire rating has to be higher. If it is an open area like car parking area, the fire rating has to be low. Now, when you talk about the steel, we know there is a standard charts. We can calculate the fire load, and based on that, we can go for the fire rating. That basically gives the time to escape the occupants very easily during that period. And for that, there are design methodologies. There should be escape routes. There may be compartment through which the lifts has to operate for the high-rise building, and other cases maybe the separate stairs which is insulated from the fire areas. Now, when you talk about the composites, now here in I have shown you some of the composites. Jacketing is another issues that people are taking advantage through that jacketing. It provides high temperature. Raise this high temperature. Only thing you can have, that means on the normal steel, it buckles or started losing its ductility at 450 degrees centigrade temperature. So before it reaches that, we want to insulate by various means, maybe vermiculite, maybe the intumescent coating, maybe the gypsum board, all those things. But when you are composites, the material, if you are selecting the composite material in such a way as an envelope to the outside, which has got a higher temperature gradient, I have shown in one of the figures that you have seen the polymer is at the top, depending on the type of polymer, that is a patch. And then when you are going for the glass reinforced polymers, or the composites, it has got a highest level of fireproofing or the high temperature applications. So there, this situation is very complex. You have to case basis, you have to find out all these parameters, and then only you have to come to the conclusion. But again, this has to be done through with the materials characteristics. that I do not know what material you're talking about, but you can write it to me and we can discuss separately.
Okay, thank you very much.
Thank you, sir, for joining our program and taking my invitation.
Okay, sir. So moving to the next session. Thank you, sir.